Welcome back to the deep dive. Today, we are focusing entirely on the systems that underpin almost every quantitative decision, these supervised regression algorithms.
Yeah, absolutely.
This is really the heart of predicting numerical outcomes in machine learning. We want to get beyond just definitions and, dive into what makes these models tick and sometimes break.
That's exactly right. I mean, if you're predicting anything like housing prices, revenue forecasts, maybe even how many staff you need,
Yeah.
you're relying on regression.
Right.
And we are, as you said, in the supervised learning camp here. So the model has a kind of instructor. You feed it the inputs, the X's, and crucially, the known correct output, the Y.
And the central challenge isn't just training the model, right?
Yeah.
A core mission of regression is, well, it's a constrained optimization problem, isn't it?
It is.
We're hunting for this functional relationship, YF by 1 by 2, et cetera, that minimizes the error on the data we trained it on. But also, this is key, ensures that the model is robust. We don't want it just memorizing the past. It has to generalize reliably to new stuff it's never seen.
Yeah, generalization. That's the goal. It's what separates a genuinely useful model from one that just overfits the training data. And since we're predicting a numerical result here, not like classification where you predict a category, our first step has to be understanding how we measure failure or error.
Okay, let's unpack this starting with the math, the error itself.
Right. So the foundation is the residue, or you can just call it the error. It's basically the distance between the actual real value y and the value the model predicted y.
Right.
And how we add up or aggregate those individual errors that really defines our approach.
Our sources lay out 3 really critical metrics that tell you the story of your model's performance: SSE, MSE, and MPE. So SSE is the sum of squared errors.
Yep.
And that's what a lot of linear models are fundamentally trying to minimize, isn't it?
It is. And MSE is just the mean squared error, the average of those. The key insight, I think, with squaring the errors is that it hugely penalizes the big mistakes.
Right.
It forces the model to worry more about those, significant outliers than just the little bits of noise.
Which is useful, definitely.
Yeah.
But it only tells part of the story. If you only look at squared errors, you don't know if your model is consistently, say, overshooting or undershooting the target.
Exactly. That's where MPE, the mean percentage error, comes in handy. Because it uses the actual values, not absolute ones, MPE acts as the sort of instant diagnostic for bias.
Bias, okay.
Yeah, it tells you if your predictions have a consistent systematic slant one way or the other.
Gotcha. So MSE tells you how big your mistakes generally are, while MPE tells you which way your model tends to lean, if it does. They're diagnostics, really, helping you move beyond just one single score.
Precisely.
Okay, so with that error framework set, let's look at the foundational algorithm. Ordinary least squares regression, or MLR. This sounds like where simplicity meets, strictness.
MLR is definitely the workhorse. It calculates those coefficients by mathematically minimizing that sum of squared errors, the SSE we just talked about. We call it statistically linear because the parameters, the betas, are combined linearly. And its big advantages are, high interpretability, it's fast, and it doesn't hog memory. Very efficient.
But there's always a but, isn't there? That efficiency comes with a pretty big asterisk. MLR relies on some huge assumptions.
Oh, definitely. It presupposes linearity in the underlying relationship. It assumes the connection between your inputs and output is basically a straight line.
And constant variance of errors, too, right? That homoscedasticity thing.
Yes, exactly. It assumes the spread of the errors is consistent across all levels of your input variables. And crucially, it's also extremely sensitive to outliers.
Right, like your example, run a housing model for a regular neighborhood, and suddenly there's a castle in the data.
Exactly. That one single observation can totally skew your linear function, pulling it way off course for all the normal houses. If you violate its assumptions, the model can really break down.
And here's where the conversation gets really interesting, I think, because that sensitivity is precisely what often leads to overfitting. That moment where your model gets too good at fitting the training data, capturing all the noise, and then it just fails catastrophically when it sees new real-world data.
And the fix for that is regularization. It's all about managing that critical bias variance trade-off. We basically introduce penalty terms into the calculation designed to constrain those coefficients, keep them in check.
Okay, so how do we do that? I know ridge regression is a big one that uses an L2 penalty.
Correct. Ridge constrains the sum of the squares of the coefficients. Think of it like adding a little bit to the cost function for every coefficient that gets too large. This helps dampen extreme values, making the model less sensitive, especially if your input features are highly correlated, that multicollinearity problem.
Okay, so ridge dampens things. And then there's LASSO, the least absolute shrinkage and selection operator. That uses an L1 penalty.
Yes, and this is where I think it gets really clever. By constraining the sum of the absolute values of the coefficients, LASSO does something Ridge doesn't. It can force some coefficients all the way down to 0.
Ah, so it actually eliminates features.
Exactly. It doesn't just reduce complexity by shrinking coefficients, it acts as an automatic variable selection mechanism. It literally weeds out the features it deems useless for the prediction.
So if ridge is sort of gently pulling coefficients back towards 0, LASSO is actively pruning some of them out entirely.
That's a great way to put it. And of course, if you find you need a bit of both, some shrinkage for stability and some feature reduction, there's Elastic Net. It basically gives you a knob to blend both the L1 and L2 penalties.
Okay, that makes sense. Now, what if the underlying relationship just isn't linear at all? We can move beyond straight lines, right? Like polynomial regression?
We can. Polynomial regression lets you model curves by using a nonal degree polynomial. So instead of y equals mx plus b, you might have y equals 2 plus bx plus c, or higher powers.
But wait, you mentioned earlier, there's a subtlety there, isn't there?
Yes, good catch. We need to slow down on that one. It's a crucial distinction. Polynomial regression might look like a curvy line on a graph, visually nonlinear, right?
Yeah.
But it's still considered statistically linear. And that's because it's linear in terms of the parameters, the betas. Think about 1 dial O's by 2 plus beta dollars. The variable x is squared, sure, but the coefficient beta $1 is still just a simple multiplier. It's being combined linearly.
Ah, okay. So the linearity refers to how the coefficients are used, not necessarily the shape of the final line.
Exactly. Even if the feature itself is transformed, like being squared or cubed, the model structure in terms of how it uses the betas is still linear.
Got it. That clarifies things.
Yeah.
And then if you're dealing with, say, count data, like number of website clicks or insurance claims.
Right. For counts, you often move into the family of generalized linear models, or GLMs. Poisson regression is a common choice there, specifically designed for non-negative integer outcomes.
Okay. But what if the shape is really complex, really wiggly, and we don't want to assume a polynomial form?
Then we move into truly non-parametric models. These don't assume a specific functional form beforehand. A great example is Mars multivariate adaptive regression splines. It's designed to automatically model nonlinearities and interactions between variables.
Mars. How does it actually achieve that flexibility? It sounds complex.
Well, it uses these things called hinge functions. You can think of them like flexible little building blocks, mathematically something like max x text cancel, x text cancel.
Functions like thresholds?
Kind of. They effectively split the data space into different regions, and Mars fits simple linear segments or splines within each region. It pieces these together, allowing it to capture really complex nonlinear patterns by combining many simple pieces.
Interesting. So it builds complexity from simple parts. What about LOES? Locally estimated scatterplot smoothing. Sounds similar.
It's also nonparametric, yeah. LOES works differently, though. Instead of building a global model from pieces, it fits a low-degree polynomial, often just linear or quadratic, locally.
Locally, so just to nearby points.
Exactly. For any point where you want a prediction, it looks at its neighbors in the scatter plot, gives more weight to the closer neighbors using weighted least squares, and fits a simple polynomial just to that local neighborhood. It's like calculating a sophisticated rolling average tailored specifically to where you are on the graph.
Okay, that makes sense. It adapts to the local structure.
Okay.
Let's shift gears a bit, moving from fitting functions to, well, predicting by memory. Thinking about instance-based models like k-nearest neighbor, KNN, for regression.
KNN. Conceptually very simple, but can be computationally quite intensive. It's called instance-based because it literally stores the entire training data set. No real training in the usual sense.
So how does it predict?
When you give it a new data point to predict, it searches through all the stored training examples, finds the k examples that are most similar, the nearest neighbors based on their features, and then it predicts based on their known y values, usually by averaging them, or maybe a weighted average where closer neighbors count more. Prediction by local consensus, basically.
Prediction by looking up the most similar past cases.
Okay.
And you mentioned There's a surprising side use for K and N.
Yeah, it's actually a pretty neat technique for imputation of missing data. If you have a missing value for one feature in a data point, you can find the K nearest neighbors based on the other features, and then predict the missing value based on the values those neighbors have for that feature, using similarity to fill the gap.
Clever. But K and N isn't perfect.
Yeah.
Right? What are the downsides?
Well, its main struggles are with scalability and high dimensionality, the curse of dimensionality. If you have a huge number of observations, finding those nearest neighbors for every prediction can become very slow. And its accuracy really depends heavily on having dense, well-structured data. If your data is sparse, the whole concept of nearest neighbor can become a bit meaningless.
That inefficiency, I suppose, is often why we turn to the incredible power of ensemble methods. These algorithms designed specifically to combine the strengths of multiple models.
Absolutely.
Yeah.
Combining models or ensembling almost always improves stability and accuracy compared to using a single model. Random Forest is a classic example.
Right, random forests build lots of decision trees.
Exactly. It trains a whole multitude of independent decision trees, each on a slightly different subset of the data and features. Instead of relying on just one tree, which can be quite volatile and prone to overfitting, it takes the average prediction across all the trees in the forest. This averaging smooths out the variance and corrects that tendency of individual trees to latch onto noise.
Okay, so averaging for stability. And then we have the sequential powerhouses, the boosting methods like GBM and XGBoost. These work differently, right?
Very differently. This is where it gets quite tactical. Unlike random forests where trees grow independently, boosting adds weak predictors, often simple trees, one by one, sequentially.
And the key is that each new predictor tries to fix the mistakes of the previous ones.
Precisely. Each subsequent predictor focuses on correcting the errors, or technically the pseudo-residues, that the ensemble so far has made. It learns from the mistakes of its predecessors.
And XGBoost is kind of the king of the hill there, often. What makes it special?
XGBoost, or extreme gradient boosting, has become a benchmark, partly because it takes that sequential correction process and integrates sophisticated regularization terms like L1 and L2 penalties we discussed earlier directly into the boosting process.
So it builds in protection against overfitting for the whole ensemble.
Exactly. It helps prevent the entire complex ensemble from getting too tailored to the training data. It's known for being both highly accurate and pretty well disciplined.
Okay. Now, if we're talking about maximum complexity handling really intricate patterns, we inevitably land at artificial neural networks, specifically maybe the multi-layer perceptron, or MLP.
Yes, the MLP is a fundamental type of feed-forward neural network. You have at least 3 layers: an input layer, one or more hidden layers, and an output layer. Training typically happens via backpropagation, where errors are fed back through the network to adjust the connection weights.
And they use nonlinear activation functions in those hidden layers, right? That's key to modeling complexity.
Absolutely crucial. Those nonlinear functions allow the network to learn and represent incredibly complex nonlinear relationships between inputs and outputs.
Okay. And is MLP the only relevant ANN for regression? I've heard of radial basis function networks, RBFNs.
RBFNs are another type, yeah. They tend to have simpler designs and can train faster than MLPs in some cases. They work quite differently. Instead of backpropagation adjusting all weights, an RBFN typically calculates the Euclidean distance from the input data point to a set of stored prototype vectors, or centers. Then, a radial basis function like a Gaussian kernel is applied to that distance.
So it's based on distance to known patterns.
Essentially, yes. It creates these zones of influence around known prototype patterns stored in the hidden layer. If a new data point falls close to a particular prototype, the output associated with that prototype gets weighted more heavily.
Interesting. Sort of like a more complex, function-based version of nearest neighbors in a way.
You could loosely think of it like that, yes. It's about similarity to learned centers.
Okay, wow. We've covered a massive spectrum of methods here, but there's one specific regression challenge we absolutely have to touch on: time series forecasting, where the variables are indexed over time. That's a whole different beast, isn't it?
It really is. The time dimension adds significant complexity. The classic time series approach, for decades, was the ARIMA model, autoregressive integrated moving average.
Right. And ARIMA predicts based on past values and past errors.
Yeah, it uses past values of the series, the AR part, and past forecast errors, the MA part. But here's the critical limitation. Standard ARIMA requires the time series to be mathematically stationary.
Stationary meaning no trend, Constant variance, no seasonality.
Exactly. And let's be honest, real-world business data sales, web traffic, inventory, it almost never adheres to that strict stationarity assumption out of the box.
Which is why newer models like Profit, developed by Meta Facebook, have become so popular, right? It kind of throws out that need for stationarity.
Pretty much. Profit was designed specifically to handle the kinds of time series data that business analysts actually encounter data with trends, multiple strong seasonalities, like weekly and yearly, and holiday effects.
So how does it work? What's the practical insight?
The key is that Profit is a non-linear, decomposable model. It explicitly models the time series as a sum of components, YTT plus ST plus HT plus epsilon.
So GT is the trend.
Yep. The long-term growth or decline, GLers, it can even automatically detect and adjust for change points in the trend.
Okay. And GRST is seasonality.
Right. UST captures periodic patterns like day of week or time of year effects, and UST specifically models the impact of holidays, which often don't follow regular seasonal patterns. The epsilon is just the error term.
So it breaks the messy reality down into understandable pieces.
Exactly. And it handles all this pretty automatically. You don't usually need to manually detrend or deseasonalize your data first, which is a huge practical advantage for practitioners dealing with complex, volatile forecasts.
That makes a ton of sense. Huge time saver. Okay, so we've got this massive toolkit now, from simple linear models to complex neural nets and time series specialists. How on earth do we choose the ideal algorithm for a given problem? What characteristics should we really prioritize?
Well, often it comes down to evaluating across, say, 4 key performance pillars. First, speed. And specifically, fast prediction speed is often critical for real-time systems, even if the initial training takes a while.
Okay, prediction speed. What else?
Second, stability. How sensitive is the model to outliers or small changes in the data? Less sensitive models often mean less time spent on laborious data pre-processing.
Makes sense. Third,
Third is naturally accuracy. Achieving that Goldilocks fit, not underfitting, not overfitting, but generalizing well.
right. And fourth,
Fourth, and increasingly important, is efficiency, especially limited central memory usage. This is absolutely non-negotiable if you're deploying models on resource-constrained devices like mobile phones or embedded systems in IoT.
good point. Performance is key, but what about usability?
Absolutely. Beyond raw performance, the model needs to be usable. The specialist, the data scientist, needs to understand its basic assumptions, how it works conceptually. But I think increasingly we're also prioritizing algorithms that can automatically select the most useful properties or features.
This loops back to LASSO and Friends, doesn't it?
Exactly. Algorithms that perform automatic feature selection like LASSO, Ridge can help a bit too by shrinking less important features, and also things like principal components regression, PCR.
PCR uses PCA, principal component analysis, to reduce the features first.
Right. It uses PCA to boil down the input features into a smaller set of uncorrelated components that capture most of the variance, and then runs regression on those components. All these methods become really indispensable because they reduce the burden of intensive manual feature engineering.
Which can be incredibly time-consuming and require a lot of domain expertise.
Totally. So this kind of brings us back to a foundational wisdom in modeling, often summed up by Occam's razor. Simpler explanations are generally better.
Keep it simple.
Yeah. Simpler models are typically preferred, all else being equal, because they tend to be more robust, they're easier to interpret and explain, and they naturally help you balance that tricky bias-variance trade-off we talked about. They achieve useful complexity not just by adding tons of parameters, but often by being smart about pruning away the irrelevant inputs.
Okay, so we've journeyed all the way from the strict mathematical world of MLR through the automatic segmentation of Mars, the variance reduction of random forests, and the specialized decomposition of profit for time series. You, listening, should now have a much more comprehensive framework for understanding numerical prediction in ML.
And if we connect this back to the bigger picture, remember that the algorithms we highlighted as being particularly powerful and efficient, like LASSO, like PCR, they really achieve their stability and strength by automatically reducing the complexity, the dimensionality of the input data itself. They essentially make the human's job of selecting the right features less manual, more automated.
Which raises a really interesting, maybe provocative thought for you to take away. If these sophisticated algorithms are getting better and better at automatically selecting the most valuable features from these huge, messy data sets, how does this shift the essential role of the human data scientist? Does our job maybe move away from the nitty-gritty of manual feature engineering and pivot more towards defining the overall problem accurately, managing the business context, understanding the ethics, and ultimately choosing the right level of complexity for the task at hand? Something to chew on as you start applying these insights.